Welcome to The Explainer. I am absolutely thrilled you're here because today we are going to demystify the hidden math of organizing our world. Have you ever looked at a bookshelf, a lottery ticket, or, even a team of your coworkers and wondered exactly how many different ways they could be arranged? It feels a little like magic, but it's actually rooted in two absolutely foundational concepts: permutations and combinations. And by the end of this, we are going to master them both.
Now, if you have any math anxiety at all, just take a deep breath. We've got a really clear roadmap to get us from the basics all the way to the advanced stuff. First up, does the order matter? Second, factorials in the formulas. Third, arranging books on a shelf. Fourth, building teams of engineers. And finally, the Mississippi problem.
Okay, let's dive into this. Section 1. Does the order matter? Establishing the golden rule.
This is literally the most critical concept in this entire explainer. Whenever you're looking at a group of items, tackling a word problem, or just figuring out a real-life scenario, I want you to stop and ask yourself this one deceptive but foundational question. Does the order matter? The answer to that question determines absolutely everything you do next.
If the answer is yes, you're dealing with a permutation. A permutation is all about arranging things in a very specific order. Position matters. Think of a combination lock, which actually, scratch that, it really should be called a permutation lock because the order of those numbers absolutely matters. On the flip side, if the order doesn't matter, you have a combination. You aren't arranging, you're simply pooling or combining items together into a group.
And this brilliantly illustrates the difference. Let's say we have 4 letters, A, B, C, and D, and we want to choose just 2 of them. If we're arranging them as permutations, we get 12 different ways. AB is counted, and BA is counted as a completely separate thing. But when you look at combinations, there are only 6. Why? Because in a combination, AB and BA are the exact same group of letters. Duplicates where only the order changes, they just get thrown out. But making lists like that is fine for 4 letters. What if we have 40? We're going to need some tools to skip the tedious manual counting.
Which brings us to Section 2, factorials and the formulas, the mathematical engine.
Before we get to the formulas themselves, we have to define the mathematical engine that powers them, and that's the factorial. Denoted by an exclamation point, a factorial just means multiplying a number by every integer below it, all the way down to 1. So 4 factorial is simply 4 times 3 times 2 times 1.
But real quick, before we move on, I have to drop a surprising mathematical fact on you. 0 factorial, it doesn't equal 0. No way! 0 factorial equals 1. I know it sounds weird, but it's not undefined, it's just 1. If you're wondering why, well, it's basically a rule you just have to memorize so the formulas can work seamlessly.
And here they are, your magic tools. The top formula is for permutations, called NPR. The bottom is for combinations, NCR. In both of these, the N stands for the total number of items you have available, and the R stands for how many of those items you are actually choosing. Notice how similar they are. The combination formula is exactly the same as the permutation formula. It just adds an extra R factorial to the bottom, and that's there to divide out all those duplicate groups we talked about earlier.
Let's move to and see how this builds in Section 3, arranging books on a shelf, the training ground.
Let's test these formulas out. Say you want to put 3 books on a shelf from a total group of 7. Step 1, look for keywords. The word arrange immediately tells us the order is important, so right away we know this is a permutation. Step 2, we set up our formula as 7p3, 7 total books, choosing 3. Following our formula, that means 7 factorial divided by the difference between 7 and 3, which is 4 factorial. Now instead of multiplying everything out like crazy, we can just cancel out the 4 times 3 times 2 times 1 from the top and bottom. That simply leaves us with 7 times 6 times 5.
Which gives us the incredibly satisfying payoff of 210. There are exactly 210 different ways to arrange those 3 books on your shelf from a group of 7. Now, what if you're arranging 5 books, and you're choosing all 5 of them to go on the shelf? You could definitely use the formula, finding 5p5. But you can also use the fundamental counting principle as a quick alternative. Just visualize 5 empty spots. For the first spot, you have 5 book options. Once you place it, you only have 4 options left for the second spot. Then 3, then 2, then 1. Multiply those options together, 5 times 4 times 3 times 2 times 1, and you get 120 ways.
Time to crank it up a notch. Section 4, building teams of engineers, testing combinations. We are going to escalate the complexity now and deal with dynamic groups of people. Here's your scenario. You have a pool of 12 talented engineers, and you need to build a team of 4. I want you to actively engage right now and answer this for yourself. Is this a permutation or a combination? Does the order matter?
So the crucial point is that if I select John, Sue, Sally, and Chris, it is the exact same team as if I selected Chris, Sally, John, and Sue. The order doesn't matter for a team. That means it's a combination. We set up 12C4, that is 12 factorial divided by 8 factorial times 4 factorial. To save some time, we write out the top 12 factorial only down to 8, allowing us to cancel out those 8 factorials immediately. After simplifying the remaining 4 times 3 times 2 times 1 on the bottom, we're left with a surprisingly clean equation, 11 times 5 times 9.
Which comes out to 495. And hey, here's a quick mental shortcut for the math there. 11 times 9 is 99. 99 is just 1 less than 100, so 100 times 5 is 500. Minus that extra 5, giving you 495 possible teams. All right, here we go. Section 5, the Mississippi problem, the boss battle.
You've mastered the basics. You've mastered teams. It is time to deal with repeating elements. But before we tackle Mississippi, let's look at the rule for repeating letters using a slightly easier word, Alabama. How many ways can you arrange these letters? Well, step 1, count the total letters. There are 7, so we put 7 factorial on top. But step 2 is the catch. The letter A repeats 4 times. If you swap an A for another A, it looks exactly the same, right? So we have to divide those out. Step 3, divide the total by the factorial of the repeating letters. That's 7 factorial divided by 4 factorial. Okay, now you are ready for Mississippi. Step 1, count the total letters, 11. So 11 factorial goes right on top. Step 2, carefully identify the repeats. We have 4 I's, 4 S's, and 2 P's. Step 3, we set up our massive fraction. 11 factorial on top divided by 4 factorial times 4 factorial times 2 factorial on the bottom. Step 4 is canceling our terms just like we did before to bring this absolute monster down to a solvable size.
Now what's really interesting here is the sheer scale of the answer. When you finish canceling and multiplying all that out, you are left with 34,650. That's 34,650 different ways to arrange the letters in a single 11-letter word.
And that brings us to the end of our explanator. I want to leave you with this final thought. Take a second to look at the objects around you right now. The apps on your phone screen, the clothes in your closet, the people in your life. How many unseen combinations and permutations govern your daily life? You are now fully equipped with the mathematical engine to look at any group of items and calculate the possibilities. So keep asking yourself if the order matters, keep using those formulas, and keep exploring the amazing math of arrangement. Thank you so much for learning with me today.